Hello, Mr. Betts here. I want to take a look at a couple of more complicated examples using differential equations. And these are going to be kind of multi-step problems where we're actually going to be able to find the constant of proportionality, at least in this first one here. So um, let's first look at the first sentence here. And it says the number of bacteria in a culture increases at a rate that is proportional to the number of bacteria in the culture. Okay, so a bacteria culture, we're looking at a petri dish and there's thousands of them in there. Looks like tens or hundreds of thousands of them, in fact. Um, so let's first set up a differential equation that models just that part of the problem. So I'm going to call the number of bacteria here. We're not told in the problem, so we can make it up. So the number of bacteria in the culture, I'm just going to call n. So the change in the number of bacteria in the culture with respect to time is going to be proportional to the number of bacteria in the culture. Okay, so we have this differential equation here, and that's modeling the situation with the growth of the population of bacteria. Now, this next part here says after 2 days there are 150,000 bacteria in the culture, and the number is increasing at a rate of 50,000 bacteria per day. So we can take this information and plug it into this equation because both of these numbers that were given to us, we actually have in our equation. So it says after 2 days, there are 150 bacteria in the culture. That's going to be a number of bacteria at some particular time. It also says that at a particular time, at this particular time, the number of bacteria is increasing. So number is increasing at a rate of 50,000 bacteria per day. That right there is a rate which represents dn dt. So by plugging the 50,000 in for dn dt and the 150,000 in for n, we can use that to solve for k. So we get k is equal to, we divide by 150,000, reduce that, you get 1/3. And so our differential equation now becomes dn dt is equal to 1/3 times n, or you could say n divided by 3. So by having some information about how fast the population is changing at some particular time and how many bacteria are in the culture at that time, then we're able to solve for what's called the constant of proportionality, that k value, and we get a differential equation that is much more specific now. Okay, in our second example here, we want to write a differential equation that relates the position of an object and its distance to the center of the Earth. So here's what's going on. So we have this guy that was studying gravitational force. I'm not going to give his name, but you might know who he is. So a polymath is somebody who's generally good at a lot of academic areas. So this is the guy who contributed to a lot of sciences back in his day. And he discovered that the accelerating force of gravity between two objects is inversely proportional to the square of the distance between the centers of the two objects. Okay, so the accelerating force of gravity is inversely proportional to the square of the distance between the centers of the two objects. So the distance between an object orbiting Earth and the center of Earth is given by this variable r. And we're going to assume there's no air resistance, so the object is, say, the moon or the International Space Station up where there's no air resistance. So first of all, let's keep in mind that acceleration is a rate of change. So remember, acceleration is the derivative of velocity. And so what I'm going to do is, with this accelerating force of gravity, I'm going to say dv dt. Okay, so that's the accelerating force of gravity, and it's inversely proportional. So we're going to have some constant divided by, it says, the square of the distance between the two objects. So divided by r squared. And that's it. So that's the gravitational equation right there. This is actually a really important gravitational equation. Using this, you're able to calculate the orbits of the planets and the orbits of the moons, and figure out, how fast things are going to accelerate toward Earth or toward other planets. So this is a really important equation, especially once we're able to solve this. So this is what being a differential equation is going to have a solution that will give us the velocity of an object at a given time based on this gravitational constant. I do also want to mention that this guy who discovered this relationship between gravity and mass of objects, distance of objects, the gravitational constant depends on the mass of the objects, did co-invent calculus. So in his time, he and another guy kind of independently came up with calculus ideas that relate differential calculus with integral calculus. And so you can blame them for all the calculus you get to learn today.